This is Mr. Martin. This is part 2 of section 10.8 video notes. We just finished talking about the chord-chord power theorem and the tangent-secant power theorem, and I just wanted to emphasize here that it's the square of the tangent segment, and it's the product of the entire secant segment and its external part. So it's just the part outside the circle. So keep that in mind, and I'll mention that again when we do the example problems. We could prove this third power theorem in a similar manner using triangles, similar triangles like we did with the other two. But I think you probably have the point after we did two examples. So let's go ahead and write out the secant-secant power theorem. And again, if you need to use this in a proof, you would just write secant-secant power theorem. And this one says, if two secant segments meet at a point outside a circle, then the product of the secant segments and their external parts are equal. Alright, so let's take a look at what we're looking at. We've got the two secant segments, so that's Sn and Sp. And then we've got the two pieces of the secant segments outside the circle, so that's going to be Sr and Sq. So again, whenever you're working with these secants and these power theorems, make sure that you're using the outside parts. So this power theorem would say that Sn, which is the top secant segment, times Sr, which is its external part, so the product of those, would be equal to Sp times Sq. Alright, and again, when you use it in a proof, just write secant power theorem. So let's give a go at some example problems using these. First example, we want to find x. So we've got two chords that intersect inside a circle. So we know that the two pieces of the chords, the product of the pieces of the chords, have to be equal. So one of the chords I have 3 times x, and the other chord I have 7 times 4. So 3x is equal to 28, which would then mean that x is equal to 28/3. Alright, that's it for that one. Again, if you have questions, make sure you ask. If you want to try these on your own and then pause the video and restart it to check your answers, that's great as well. Alright, for the second one, we've got tangent and a secant, so we're going to use our tangent-secant power theorem. So it says that the tangent segment squared, so we have 6 squared, is going to be equal to the entire secant segment, which in this case is y plus 5, so be careful about that, because the entire secant segment goes from this point all the way through the circle to the other point. So, and then times the outside part, so that's times y, that's the outside part, so we're going to have to distribute here when we solve, so be careful with that. So, and I'm going to flip the sides here. So I've got y squared plus 5y is equal to 36. So I have y squared plus 5y minus 36 is equal to 0. Solve this however you like. I'm going to factor it. 2 factors of 36 that when I add them I get 5. So that's going to be y plus 9 times y minus 7 is equal to 0. So I've got y plus 9 is equal to 0. We have to use our zero product property, or y minus 7 is equal to 0. So this gives us y is equal to negative 9. So that sometimes a negative will work, but in this case I can't have a negative segment, so that one's not going to work, which means y minus 7 equals 0, or y is equal to 7. Alright, so there's that one. And then the next one, the third power theorem example, we've got a secant. So we're going to use the secant power theorem. So we know that the entire secant segment, so for the top one it's z, times the portion that's outside the circle, so that's 5, is going to be equal to, and I'm just going to show all the steps, it's going to be 14 plus 3, that's the entire secant segment on the bottom, times the outside part, so that's 3. So I get 5z is equal to, that's 17. 17 times 3 is 51. Divide both sides by 5 and I get z is equal to 51 fifths. Alright, so that's all these examples to finish up part 2 of section 10.8. Again, make sure you ask me questions if you have any, and we'll see you next time.